Hello guys, welcome to the session. Today we're going to go over glycolysis specifically in the liver because for the next videos I want to show you gluconeogenesis, and you know that gluconeogenesis just happens in the liver and in the kidneys. So this is a very good place to show everything. And I like to start very generic, very basic. And we are starting with when glucose levels in circulation start to rise, the cells are going to allow glucose to enter by GLUT transporters. And for this series of videos, we're just going to see two, GLUT2 and GLUT4. GLUT2 in this case for the liver, and GLUT2 has a high Km, which means that it has a lower affinity towards glucose, because the liver, in addition to the glucose that it will take for its metabolic processes, it will also want to take the glucose in excess that is in circulation in order to store it in the form of glycogen. But for now, we're going to see that when glucose enters the cell, in this case the hepatocyte, the thing is that as glucose enters, it could also go out because the GLUT2 transporter still recognizes it. So what the cell does is something interesting. It will change the molecule just a little bit. In this case, it will just add a phosphate. And it does this, so now the GLUT2 transporter does not recognize this molecule and does not have affinity towards it, so it is trapped inside. And also because now the cell is looking at this step as that we are decreasing the concentration of glucose inside the cell. So that sends signals to indicate allow more glucose to enter. And this step, before starting to go through the names of the enzymes, I want you to look then just by logic, not hard memorization. Just try to see the substrate, the product, and what is happening, and try to make a guess to see what the name might be. In this case, we're looking at hexose. So in that hexose, we are moving a phosphate group, in this case from an ATP to this molecule. And the generic name for molecules in which a phosphate group is moved from ATP to another molecule are kinases. So we have an hexose, and we're using kinases. So in this case, the name will be hexokinase. In this case, for the liver is 4. And its function of hexokinase 4, in addition to what I'm showing here, I'm going to say another thing when we come through gluconeogenesis, so you can see how interconnected both are, glycolysis and gluconeogenesis. But for that, I'm going to wait for later. So we remember that in here, we use energy in the form of ATP with a magnesium cofactor in order to make this step to proceed forward and be irreversible, to be favorable. So now that we have glucose 6-phosphate, the cell is going to transform it into fructose 6-phosphate. And on here, let's stop for a minute. We have an hexose, and now we have a pentose. So we changed the arrangement of the atoms in the molecule. So we did an isomerization. In this case, the enzyme is going to be called glucose 6-phosphate isomerase. And the logic behind this step, I want to wait a little bit when we come on here and on this step, in this step, so you can make the connection why the cell does this step in glycolysis. For now, fructose 6-phosphate will be transformed into fructose 1,6-biphosphate through the enzyme phosphofructokinase 1. And for phosphofructokinase 1, what you need to know is that it is not hormonally stimulated directly. There is another one called phosphofructokinase 2 that is. And for that also, I'm going to wait for gluconeogenesis because I want to show you how hormonal stimulation, specifically from insulin and glucagon, plays a role, and big role, in regulating this step of glycolysis. But I'm going to wait a little bit for that. And on this step, we also are using energy in the form of ATP to make this step favorable and irreversible. So once we, and another thing, this step is called the rate-limiting step of glycolysis. Why? Because fructose 1,6-bisphosphate, this acts as a positive feed-forward activator towards the last enzyme in glycolysis called pyruvate kinase. And now fructose 1,6-bisphosphate is going to be cleaved into two, into glyceraldehyde 3-phosphate and DHAP. Called dihydroxyacetone phosphate. And now we can look at the logic in here. But this step, this cleavage is done by aldolase. And now we can see the logic behind this isomerization to go from a glucose to a fructose. The reason for that was that by doing so, on here, the carbon number 1 in fructose, it is easier to be phosphorylated in order to form this. And also, for the next step, that isomerization, what caused was that now we have a pentose that is more symmetric. So it is easier to be cleaved and to be cut into two trioses. And on here, DHAP also can be converted into glyceraldehyde 3-phosphate. Well, we could do the transformation here and go all the way and do like 2 Peyote phases, but we are not going to do that. We are just going to take that this Peyote phase counts as 2 per glucose. So, and also, glyceraldehyde 3-phosphate, remember that even though we are trying to make it shorter, so for simplicity reasons, remember that G3P, there is another molecule that also can be called G3P, that is glycerol 3-phosphate. So don't confuse it, just keep it simple on here, but be aware of that this is glyceraldehyde 3-phosphate. But there is another molecule that it is also abbreviated G3P. In this case, glyceraldehyde 3-phosphate, it is going to be transformed into 1,3-biphosphoglycerate in what is called the first energy yielding step of glycolysis. But for that, I'm going to tell you in this one the name of the enzyme. The enzyme that does this step is called G3P dehydrogenase. And as before, let's look at the name of the enzyme. Let's try to rationalize what is happening. Well, we have a dehydrogenase. What does it mean? It means that we are taking a hydrogen from one molecule and placing it in another. That molecule that is being removed, the hydrogen, it is being oxidized. So my question is, what is the oxidizing agent that works in catabolic processes that you know, that it plays a role on here in glycolysis? That is NAD+. NAD+, it is an oxidizing agent, so it itself will be reduced and form NADH. The thing is that this step is called the first energy yielding step of glycolysis because even though this is not ATP, NADH later can go into the mitochondrion and donate its electron and proton and to the electron transport chain and create a concentration differential gradient that allows between the intermembrane space and the matrix that allows ATPase to propel its machinery. Once ATPase can propel its machinery, it will start produce ATP. So here we will go through 1,3-biphosphoglyscerate to 3-phosphoglycerate. And here we will have that the enzyme that does this is a phosphoglycerate kinase. The logic behind this step before that we did, in addition to get this NADH, was to create a higher energy intermediate, 1,3-phosphoglycerate. A higher energy intermediate is capable of donating one of its phosphates towards an ADP to create an ATP. And that is what it does here. In this case, we'll donate one of its phosphates to ADP to form ATP. And remember, we are seeing 2 Peyos phases per glucose at a time. All this that we did before until here, it is called the investment phase because we use energy in order to create these high energy intermediates that are able to do this. Later, these 3-phosphoglycerate, and this step, it is the first, something that you need to know. First substrate level phosphorylation. Three phosphoglycerate can be converted into 2-phosphoglycerate after this through an enzyme called phosphoglycerate mutase. What a mutase does is that it moves functional groups from one place to another in the molecule. Once we have this 2-phosphoglycerate will be converted into phosphoenol pyruvate, abbreviated PEP, through an enzyme called enolase. And this phosphoenol pyruvate, it is also a high energy intermediate that is able to donate one of its phosphates to ADP to form ATP. So we're going to have more ATP, 2 in this step per glucose to form pyruvate. And the enzyme that does this step is called pyruvate kinase. One thing that you have to know about this step is that this step is going to have a enol intermediate that is later going to be transformed to the keto form of pyruvate, because the keto form of pyruvate is the one that later can go into the mitochondria and will continue, in that case, for aerobic respiration.